Hello everyone, welcome back to the 71-day course for seed preparation. As you are aware, in this lecture series of 71 days, we are going to cover the entire syllabus of seed examination, which includes both Part A and Part B. Let me briefly take you through the overall structure so as to understand the context of today's lecture, which is day 17. So firstly, as you can see, we have divided the complete 71-day course into two parts, Part A and Part B, just like the seed examination pattern. In Part A, we have four modules which include analytical aptitude, visual and spatial reasoning, logical reasoning, and then the design knowledge and creativity. Similarly, there are four modules even in Part B, which includes the foundation and basic concepts, core skill development, application techniques, and finally question solving skills. So there are four parts in Part B as well. Today, the topic for today, that is day 17, we are focusing on the logical reasoning part in the subject of logical reasoning, which we are doing from day 15 till day 22. Today we are in day 17, that would be gates and pulleys, which in you can also term it as mechanical reasoning, because these are some mechanical systems, gates and pulleys, and there are logical reasoning based questions wherein the question is asked with respect to gates and pulleys, and this is one of the most frequently repeated type of question in both seed and also USEED examination. You can expect at least one question, and majority of these questions are of numerical answer type questions in the examination. We will solve past seed questions as well. Some other additional questions as well will be, which are non-seed questions. We'll also practice those additional questions. But remember, majority, not always, but most of the times the questions would be of numerical type. Let me talk about the types of questions we have in this particular topic of gates and pulleys. So there are three main models of questions. If you look into the past 10 years of papers of seed and also similarly USEED and other similar examinations, you will find that majorly there are three types of questions which are asked with respect to the mechanical reasoning of gears and pulleys. First one would be the direction of turn. As you are aware, in pulleys, a disc, basically a pulley is a kind of a disc on which a rope moves. There are two types or two turns, two types of direction of turn. One is clockwise and anti-clockwise. So there are questions based with respect to that, clockwise and anti-clockwise. They would be giving you a set of pulleys or a system of pulleys, which could be a simple or a complex one, and questions would be asked with respect, and they would also be mentioning the direction of applied force and some additional external loads. Questions are mostly in this first model, questions are based on understanding the rotation or the direction of rotation, which would be clockwise or anti-clockwise in nature. So these are just visualization based questions. There is no math or calculation involved in this first model. The next two models, the second one, it includes the force and distance calculations of pulley. Now this is kind of a numerical part wherein some set of pulleys would be given, an external load would be given, and they can ask you the force required to lift up that particular load, or they can also ask you with respect to the distance, how much, if you apply a particular force, what is the distance which the load moves. Obviously it is not even though it involves math, it is not something which requires a lot of knowledge of physics as such. It is based on simple reasoning itself, so you need not worry about that. Whatever is important from seed level, from USEED seed examination concepts, that is what we're going to focus on the lecture. Obviously, we're not with respect to pulleys itself, you can study a lot about the physics of it, but that's what we're going to focus on. We'll focus on the basics which are important for the design examinations. The third model of questions are with respect to the discs and gates and the belt driven discs and gates, a relation in terms of the number of turns and the rotational velocity. There are questions with respect to that, both numerical and theoretical questions can be asked from that part, MSQ, MCQ questions. So this is one of those topics where you don't only have numericals or don't only have theoretical questions, it would be a combination of all these. The first model we are going to focus on, that is predominantly MCQ or MSQ based part, so it is more of theoretical in nature. So we'll be looking into these three models. So the way we go about it, we'll take up a typology, look into some basic principles you have to remember, look into some practice questions of different models and apply those concepts, and then we'll move on to the next concept. That's how we will be looking into this topic of gears and pulleys. So with that, let me begin with the first part, that is understanding the direction of turn. So As I told you, this is more of a visualization and understanding the direction of turn. In Pulleys, it's more of a visualization, and there is nothing as such with respect to mathematical calculations involved in it. So for instance, if we say have a simple discussion, let us say this is a fixed pulley which is fixed to the, let us say, rigid support ceiling. Now there are types of pulleys, fixed and movable pulleys. We'll study about that in the force distance calculation, because as far as direction of turn is considered, that doesn't make a huge difference. Understanding the types of pulleys and pulley systems, we'll look into that in the second part. For now, you can just understand a simple say example, something like this. Let us say there's a pulley and a rope moves over it. Let us say there's a load and you apply some force over here. Now what would be, if you want to lift up this load, what type of rotation? So there are only two types of turns which are possible: a clockwise rotation or an anti-clockwise one, and it can be simply visualized, easily visualized. Even in this case, for instance, if the rope is moving in this direction, the pulley has to rotate or turn in this direction, which would be an anti-clockwise rotation. So just visualization by understanding what is the movement of the rope, and with respect to that rope, so however the rope is moving, so if the load is lifting up, the rope has to move in this direction, the pulley also will rotate in that direction. So that is anti-clockwise. So a similar combination, they can give you a complex setup and ask you questions with respect to the type of rotation. All you need to do in this model is look into the rope and the way it moves, and accordingly you can give the answers. Let us look into some simple questions on from past CEED and also similar examinations to understand how to solve and what type of questions can be asked. This is a question from past UCEED examination of the year 2020. So let me read out the question for you. It is an MCQ based question. Even in the examination, the type of question will be mentioned to you, because in MSQ questions multiple options can be correct, but this is an MCQ question with only one correct option. So figure shows a clothesline attached to four independent pulleys PQRS. So this clothesline where you dry your clothes, that is being hanged over four pulleys. It's a system of four pulleys basically, which are all independent PQRS. Which of the following options represents the correct rotation of the pulleys that would result in lowering the clothesline? So this clothesline has to be lowered. Which is the correct direction of rotation? That's what they're asking. Which options is the correct rotation of all the four pulley system? They have given some diagrams with arrows of clockwise and anti-clockwise nature for all the four pulleys. We have to select the correct option. Now let us try to have an observation over here. The clothesline, it has to move down. That's what lowering of clothesline they're saying. So it has to move down. So first thing is to understand what is the movement of the load. So the load in this case is the clothesline that is moving in the downward direction, that has to be lowered. Now first thing, so the complete setup of the clothesline, that has to move downwards. There's a knot over here and the thread moves on these pulleys. So first, if you observe on the right hand side, we can have an observation both right hand and left hand side. Firstly, if you have an observation on the right hand side, for this to be lowered, this particular rope over here, so it's a continuous rope which is passing over the complete clothesline. Now let me tell you one thing. This particular clothesline to function even more smoothly, if you observe, so there's a knot over here, the clothesline has to be lowered downwards. So you're going to release this rope from here. So the rope on the top, that has to move in this direction, and also for this part to be lowered, there is some sort of movement which should occur at this point also. In such setups, generally we use a movable pulley. So if you can install a movable pulley at this point, the system would be even more smooth in functioning. However, so understand, so the reason I'm talking about movable pulley here is, remember that there is some movement of rope over here as well. The rope has to change its length, right? So anyways, for this to be lowered, there has to be movement of the rope in this direction. Let us look into the pulley R first. So this is the first one. Let us have an observation at R. The rope has to move in this direction, like I said, right? So for rope to move in that direction, the pulley also should rotate in the same direction I told you. So this would be an anti-clockwise rotation. In pulley R, because the rope has to move in the direction leftwards from here, so there has to be a rotation of this direction, anti-clockwise in nature. Let us see for R, here they have mentioned it as clockwise. Here also it is mentioned as clockwise rotation here. So C can be an answer. R also is mentioned as clockwise. So Just by looking into R, you can identify that answer for this particular question has to be C, because at R there should be an anti-clockwise rotation. But let us have a look at the other four pulleys also to have a surety and understand if we are thinking in the right direction or not. Now the rope has to move in this direction. At Q also there should be a movement in the downward direction, because see, I told you this, at this particular connection there will be an increase in length, there has to be movement downwards, right? So at Q, this is the pulley, the rope has to move in this direction, so there has to be an anti-clockwise rotation again. So at Q there is an anti-clockwise rotation. Now looking into P, if you look at the pulley P, so this part now, because of this movement towards the left side, we can visualize that the clothesline, the left part of the clothesline, that can move downwards, but the right part, so it has to be it has to move downwards with a balanced position completely. So this knot, because it is tied over here, this has to come down. So if you observe at S, if you look into pulley S, because it is tied over here, the rope has to come down. So the rope has to move in this direction at S. If this is pulley S, the rope has to move in this direction. So the pulley also moves in this direction. That would be a clockwise rotation. For S, it is clockwise rotation in our option. That is also correct. So let me mark for your reference. This is anti-clockwise, anti-clockwise, and for S it is clockwise. And at P, if you observe, now this rope, as I told you, it has to move in this direction. So this rope has to move. So if you observe, at this particular point where the clothesline is being attached to this loop between P and Q, if I erase these dots for you, so at Q there is a movement of rope in this direction. At P the rope is moving in the upward direction. So basically the loop itself is moving. This hook has to be lowered. So that's why I told you it would be better if you can use in practical terms, from design point of view, if you are able to use a movable pulley at this point, there would be an even more smooth transition, and also the required force would change. So what is the difference between a fixed and a movable pulley? We'll have a discussion on that moving further when we calculate the force and distance part. So I was telling you about P. Pulley P, if you observe, the rope has to move in this direction, so it has to move upwards over here, and then it has to move towards the right. So what type of rotation would this be? It would be a clockwise. So we have at R and Q, it has to be anti-clockwise. R and Q both are anti-clockwise only in option C. So right away, just by looking into one first pulley itself, we have understood that C is the answer, but we have understood the remaining four as well. So P and S have to be clockwise, P and S are clockwise, and the remaining two are anti-clockwise. So the correct answer for this particular question would be C. This was asked as a multiple choice question in the CEED examination, but similar examinations, similar standard of questions can be asked in CEED examination too. So that's about it. Let us look into the next one more question. This again is a UCEED question from the year 2018. This also is based on understanding or visualizing the rotation. We are not into the calculations yet. This is just visualizing the rotation and the direction of turn. So the next second question for this concept, now a complex system of pulleys is given. Let us read the question by looking into the diagram. Shown below is a combination of fixed pulleys. All these are fixed pulleys, because movable pulleys might have a different function. We'll study about it. So the given below is a combination of fixed pulleys. If the triangular load moves down, they're saying that this load, now understanding, reading the question properly is very important in the first step. Understand every step, because in such questions, particularly visualization part, every word becomes very important, which direction they're talking about. So they're saying that this triangular part is the load. Now that understanding, because they have not written which is load over here. So if they write just instead of triangular load, if they're mentioning the circular load, then the complete answer will change. So I have to read every part clearly. The triangular part is basically the load that moves downwards. How many pulleys will rotate in the same direction as the smallest pulley, including itself? The overlapping paths do not interfere with each other. So the question, it is a numerical answer type question. So in numerical answer type question, there has to be a numerical value for the answer. It can be in decimal values too, but here, because they're talking about number of pulleys, obviously it will not be in decimal points. The answer will be a whole number. Let us try to understand this question and see. So what are they asking us? They're asking how many pulleys are rotating in the same direction as the smallest pulley. First, have a look at the diagram and see where the smallest pulley is. I think this should be the smallest pulley. So including the smallest pulley, how many other pulleys are turning are having the same direction of turn as this? So first let us mark the direction of turn for each of these pulley for the complete diagram, and then at the last step we will count. It's very simple. I already told you the concept. You just need to visualize the direction in which the rope is moving. So at a particular point of pulley, whichever direction the rope is moving, the pulley also turns in the same direction. That's the concept, just like we have solved the previous clothesline question as well. So let us have a look. I'll change the color so that we can identify the letters clearly. So let us start from the load itself, because that's where we have a known movement. So the known movement is downward direction. This rope has to move in the downward direction. So look at this last pulley over here. So the pulley is over here and the rope is moving in this direction, right? It is moving in the downward direction. So the rotation which you see in the pulley, that has to be a anti-clockwise rotation. So let me mark that over here. This is anti-clockwise rotation. So I'll just draw the individual pulleys over here, and then we'll have a look, and then I'll write down the type of movement over there, right? So the first one we saw, that is anti-clockwise. Now moving further, just observe the rope and also understand the direction. So the rope is moving in this direction. It is moving in the downward direction. So the rope is moving in this direction. At this particular pulley, there will be, the rope has to move in this direction. So this has to move upwards. So let me draw the next pulley which we have. This one, there's a loop, probably like this, right? And the movement is in this direction, and this rope has to move upwards. So what is the movement? What is the direction of turn in the rope? The rope is basically moving this way. So the pulley also has to turn this way. This would be a clockwise turn in the pulley. So let me mark that over here. I'm erasing the arrows. Excuse me. This would be a clockwise turn. So the next pulley we have, the rope basically is moving in the upward direction over here. So for that, the rope has to move in this direction. So if this is the pulley, the rope is moving in this direction. So the rotation, the turn in the pulley has to be this way, which basically is a clockwise turn again. So this was the smallest pulley, and the smallest pulley's turn, we have to count how many pulleys are having a similar turn as the smallest pulley. So that's a clockwise turn. So we have to see how many pulleys are going to turn in the clockwise directions. We have done 3 till now. Let us look into the next one, the fourth one. So the movement of the rope in this direction it is. For that, the rope has to move over here. So the turn in the rope is this way. The turn in the pulley also will be in the similar direction. So this is anti-clockwise turn. So I'll be marking it as anti-clockwise turn. So now to have an anti-clockwise turn, next pulley again. So you have to do the calculus. You have to have an observation the backwards way. So in order to move the rope in this direction, this rope has to move upwards. So the direction of turn in the rope, it is basically a clockwise turn. So the pulley also should have a clockwise turn again. So you can mark this as clockwise turn. So there is a turn in the rope in this way, and this rope moves in this direction. So the pulley's turn has to be in this turn in this direction. So that's basically an anti-clockwise turn. So let me mark that as anti-clockwise. The next pulley, the rope is moving in this direction. So the overlapping part, they're saying that there's no interaction between the ropes as such. So it is all individual in nature. So moving on, the next pulley, if you observe, for the rope to move, to extend its length in this direction, the rope has to move downward. So the rope is basically moving in this turn. So this gives us a similar turn in the pulley. That would basically be a clockwise turn again. So you can mark it as clockwise turn. Next, moving on. So the direction of the rope is in this way. The rope has to move increase its length in this direction. So the turn in the pulley would be an anti-clockwise one. Over here you can see, because the rope is moving in this direction, that would be an anti-clockwise turn in this pulley. Now The rope movement is over here, which has to pull the rope in this direction in this loop. So the turn in the pulley, it is a clockwise turn over here, right? So the rope is moving in this direction. That's a clockwise turn in the pulley. So let me mark it as clockwise turn. The next one, the rope has to move in this direction. For that, there has to be a movement in the rightward direction. So the rope's movement is in this way. That's a clockwise turn. So the pulley will again have a clockwise turn over here also. So I'll just mark one arrow and write this as clockwise turn. Now for the rope to increase its length in this direction, it has to move upwards at this point. So the turn in the rope is in this way. That's an anti-clockwise turn. So in the pulley, you'll be having an anti-clockwise turn at this point. So let me mark it as anti-clockwise. Counterclockwise. Now the rope is moving in the upward direction. For that, the rope has to move in the leftward direction. So the movement of the rope is in the clockwise direction. So pulley will experience a clockwise turn at this point. So this will be a clockwise turn with the rope's movement in this direction. This is clockwise turn again. Now the rope, for it to move, increase its length in the leftward direction, it will experience a movement in the downward direction at this point. So this is the movement of the rope and also the pulley, which is basically a counterclockwise movement or anti-clockwise movement. So I'll just mark it as ACW, anti-clockwise. Excuse me. So for the rope to increase its length in the downward direction, there will be a movement in the leftward direction at this point. So the movement of the rope is in the anti-clockwise direction at this point again. So that pulley also will have a movement in the anti-clockwise direction. The rope's movement is leftwards at this point. So for this to move in the leftward direction, this rope has to extend its length upwards. So the turn in the rope is clockwise. Pulley also will be experiencing a clockwise turn. So this is, rather than calling it as a pulley based question, you can actually count it as a visualization question. You have to carefully observe and just mark the pulley. That's it. So for the rope to extend its length in the upward direction, there will be a downward movement of the rope over here. So this is the direction of the movement of the rope and also the pulley. So the pulley's turn would basically be a counterclockwise movement. So I'll mark it as anti-clockwise. For the downward movement of rope over here, there has to be an upward movement of the rope on the other side. So the turn in the rope over here is anti-clockwise again. So I'll mark it as anti-clockwise. For the pulley, so for rope to extend its length in this direction, the rope has to move over here. So the movement of the rope is in this way, which is basically it's a clockwise turn, not an anti-clockwise, it's a clockwise turn. So the pulley also will experience a clockwise turn at this point. Right, so the rope is basically moving in this way, which is a clockwise turn in the pulley. So that's a clockwise turn. The next one, the pulley is basically the rope is basically moving in this way, in this direction. So that is creating a clockwise turn in the pulley. The rope is moving in this way. So that's a clockwise turn in the pulley. Next one, the rope is, so I'll erase these over here. I think we are at almost towards the end. There are just 3 more pulleys. So if you look into this pulley over here, the rope is coming downwards and then the loop is moving upwards over here. So the movement of the rope is in clockwise orientation. So the pulley also will be a clockwise turn. The next one over here, just 3 more pulleys. So the movement of the rope is in the downward direction. For that, the rope from here also should come in the downward direction. So that would be creating a anti-clockwise movement of the rope. So even for the pulley, it would be anti-clockwise movement. I'll mark it as anti-clockwise. Now you'll need to take time and do it patiently. Even if you miss out or even if you have an error in one pulley, you'll need to rework the complete question again. And in the examination, time is of huge importance in CEED exam particularly. So the movement of because you just have 1 hour to solve the computer based test in CEED examination. In UCEED you have 2 hours, but in CEED examination it is just 1 hour you have. So you'll need to have the first time itself you'll need to answer it correctly. So the next one, the movement of the rope is in this direction, which is basically an anti-clockwise movement. So the movement is this way, right? Which is basically an anti-clockwise turn in the pulley. So I'll mark it as anti-clockwise over here. Right, and the last one over here, that movement is in the upward direction. You are releasing basically here in this complete complex setup. For the load to come down, you are releasing the rope from here. So this release of rope also is creating an anti-clockwise turn in the pulley. It is reverse, so the movement of the rope also is in the anti-clockwise direction. So anti-clockwise turn in the pulley. Now let us count and give the answer for this question. They have asked us how many pulleys are turning in the same direction as the smallest pulley, and the smallest pulley is having a clockwise turn like we discussed in the beginning itself. We are having a clockwise turn in the smallest pulley. Let us see how many pulleys, let us count how many pulleys are having a clockwise turn in this complete diagram. Starting from the load, you can count it. So let me count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11. So the answer for this question has to be 11. So it's a numerical answer type question. You just need to count the number of pulleys and give an answer. I hope we did not miss any other any clockwise one. If you count the number of anti-clockwise pulleys, just for understanding if we have not missed out marking something, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So in the beginning, even before you start solving, you can just count the total number of pulleys and see at the end just to match and understand in the because during the examination, when there's a lot of pressure on time constraint, it's possible that you miss out some pulleys in the calculation. So just before you start such questions, just count the total number of pulleys so that at the last step you can add them and see if you're getting the same total number of pulleys or not. So this is how you solve. Simple concept. Look into the movement, the direction of movement of the rope. The direction of pulley's turn should be parallel to it. It will be in the same direction. That's the only logic we have applied. So this is a past UCEED question which was asked with respect to the direction of turn in the pulleys. Next question over here. This is also a past UCEED question again. This was asked in the year 2015. Which also is related to probably the turn of the pulleys itself. Let us look into this question. This again is a numerical one. NAT question. Shown below is a belt and pulley arrangement. It's a belt and pulley arrangement. How many pulleys are rotating in the clockwise direction? So they have clearly stated. The previous one they have stated indirectly. They have asked how many pulleys are turning in the same way that the small pulley turns. Here they have clearly stated they are asking about the direction of clockwise movement. Let us look into it. It's a smaller system also. It will be easy for us to mark. Let us see. They have so here the triangular load. They have marked the direction. The rope is moving in the downward direction at this point. So the rope has to move in this direction. So this will create. So if this is a pulley, and the direction of rope is in this way, that will create a clockwise turn in the pulley I. So let me mark it over here that the rope is moving in this direction and this is creating a clockwise turn in this particular pulley. The next one, for the rope to move in the downward direction, this has to move in the upward direction. So the turn in the pulley would be parallel to that. So that is basically a clockwise turn again. So I'll mark it over here clockwise again. Now the rope has to move in the upward direction. For it to extend its length in this way, the rope has to move in the downward direction over here. So the turn is in this orientation, which in the pulley also will be in the same orientation, same direction. That would be a clockwise turn again. This is a clockwise turn again. Now for the rope to move in the downward direction over here, it has to have an upward movement over here. So the movement of the pulley also should be in the same direction. That again is a clockwise turn. Clockwise as in just like how the hands of a clock move in the same direction. So all the pulleys till now we are having a clockwise turn itself. Let us look at the next one. For the rope to move in the upward direction over here, it has to have a downward turn. So that will basically be a movement in this direction. That's an anti-clockwise turn. So this is counterclockwise. So this is not a clockwise turn. Let me mark it as anti-clockwise. The next one, the rope has to move in downward direction. For that, there has to be a movement in the rightward direction. The turn in the pulley would be in this way. That is again an anti-clockwise turn. This is also not clockwise. The next one, the rope has to move in the rightward direction. For that, the rope has to move its direction. It has to move in the upward direction over here. The turn in the pulley, it would be parallel to that movement of the rope. That would be a clockwise turn. So that's clockwise. The last, probably not last, there's one more. So the rope has to move in the upward direction. For that, the rope has to come downwards over here. this way, the rope has to come downwards and that's going to turn. So it's like this. The rope is coming downwards and then moving upwards. So that's basically an anti-clockwise turn, not what we are counting. The next one, they have already marked the direction over here that there is a anti-clockwise turn over here. So just count the total number of clockwise pulleys. That should be the answer for us. So we have 1, 2, 3, 4 and 5. So 5 clockwise pulleys and there are 1, 2, 3, 4 anti-clockwise pulleys. The total number of pulleys we have is 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have not missed out any pulleys. So the answer for this question, it has to be 5. It's a numerical type question. So you'll need to type in the exact numerical value. The answer has to be 5. There are 5 pulleys moving in the clockwise direction in this complete system of pulleys. So this is how we solve the questions which are related to the direction of turn. Let us now move on to the next model, wherein there is some math involved in calculating the force required to lift up a load in pulley system. So in order to know that, you should first understand the types of pulleys, the difference between fixed and movable pulley. Let us have a discussion on that. Even before moving towards this, you know that in these computer-based test questions, it is of huge importance to have sufficient practice on the logical reasoning questions of similar standard of CEED examination. You can access a lot of free resources on our mobile application. The link to download our KP Exam Prep app for CEED, UCEED and design examinations. The link for it is in the description of the video. You can download the app. Once you download the app, you can go to, so in order to access this complete lecture series, this is day 17. If you want to access the complete 71-day lecture series, you can install the app, go to the store tab you have, and in the store tab you have a lot of courses related to design, including CEED, UCEED, NIFT and ID. You can select the UCEED one, and there's a 71-day lecture series for UCEED examination. So you can also you can select that and apply any relative. Sometimes there are coupons available. You can also avail those offers by applying the coupon at the checkout. Once you proceed to the payment, you can select the 71-day lecture series to have a complete access for this UCEED and for the CEED exam preparation. Other than that, to access the free resources, practice tests and practice questions, and also some practice lectures, free lectures which you have on the app. For that, you can click on these 3 horizontal bars you have on the top left corner. The side tray opens up. In the slide tray, you have an option of free material. Select the free material tab, wherein you'll have a lot of free documents, free videos and tests available on our app. You can check out the relevant CEED resources. There's a folder for CEED, just like how you have for UCEED, NATA. Similarly, you have a folder for CEED resources as well, in documents, even in videos, and also excuse me, and also in tests. There are free tests of CEED examination available for you for practice. You can also access those for self-assessment and understanding of the concepts. Let us now move on to the second model of questions in pulleys and gears. The second model is focused on force and distances. So what is the use of a pulley? Basically, there are 2 functions. One, to change the direction in which you're applying a force. For example, let us say there is a well. You might have all observed, if you want to take out water from a well using a bucket. So let us say there's a bucket of water which you want to lift up. So you'll need to apply a force. So if you're basically pulling it, you'll need to apply a force in the upward direction over here. If you're not using a pulley, you'll need to pull it up. You're working against gravity. If you're using a pulley system for the same bucket of same size, if you're basically using a pulley over here and then you're applying force on that rope using this pulley, the direction of force is changing. In the first instance, without the pulley, you're working against the gravity or pulling against gravity. Here, even though you're working against gravity, the direction in which you're applying the force, that is same as the direction of the gravity. So it will be easy for us to pull it downwards rather than pulling it upwards. So to change, the first function of pulley is to change the direction. In these 2 cases, as far as the pulley system is considered, you need to apply the similar force of the weight of the bucket itself, but the direction is changing. Because of the change in the direction, you're using gravity for your rescue. Basically, in this case, here you're completely working against gravity. So the direction, practical terms, direction of force might become important, like in this example. So we can use pulleys to change the direction of the force application. That is one. Second, you can also use pulleys to have have to apply less force to have a lift of larger weight. Now for that you will need to use movable pulleys. So that's the basic difference. So there are two types of pulley systems. You have two diagrams over here. The first one where the pulley is fixed to a rigid support like a ceiling or something. Now let me also tell you one point. In all these calculations, including in the questions of CEED examination too, we assume that the pulleys are frictionless, and also the pulleys do not have any mass. So the mass of the pulley is negative, because see, if the pulley itself is having a heavy mass, its moment of inertia comes into picture. That will have an impact on the angular velocity and so on. So that will become a question with respect to the physics. We are focusing on the logical reasoning part here. So we have massless pulleys, so pulleys without any mass. We neglect the mass of pulleys, basically lightweight. Other than that, in other words, we neglect the moment of inertia of the pulleys. And other than that, we assume that these pulleys are frictionless. For example, if you can look into this question, this is a past CEED question from the year 2022. The first sentence itself, it says a system of frictionless and massless pulleys. They are asking us to neglect the moment of inertia and also neglect the friction of the rope, because if those come into picture, it would become a question of physics and not logical reasoning. So anyways, coming back to these types of pulleys over here, we have two types. The first one, this is called as a fixed pulley. Fixed pulley is something in which the pulley's position is fixed in this complete space. The position of this pulley, it is fixed at this point. It is connected to a rigid support. You're just applying force over here. Now in this fixed pulley, like I said already, like the example of lifting up water from a well, in fixed pulley, the force application, it is same as how much force is required without a pulley. For example, let us say this object is 10 kg in weight. So to lift up this 10 kg weight, the force you need to apply in the downward direction over here, that also should be a 10 kg force. It should be of same quantity. And remember, in any pulley system, the tension on both the sides, it would be same. If you're having a continuous rope, the force or the tension in the rope on the left side, on the right side, that has to be same. So that's basically considering that it's basically equilibrium. So considering equilibrium, it has to be same on both the sides. So basically, to lift up this 10 kg, you need to apply a force of 10 kg. The only change over here because of the pulley is the direction. To lift it upwards, you're applying a force in the downward direction. Right? So fixed pulleys are used for. So fixed pulleys do not have any mechanical advantage in physics. In mechanical engineering, this is called as mechanical advantage of a system. Here, there is no mechanical advantage of a system. Reason being, there is no less force you're applying. You're still applying 10 kg force to lift up 10 kg weight. So there is no mechanical advantage in this system, but there's a change in the direction. So if there's no mechanical advantage, why do we use fixed pulleys? I already gave you the example. We use it to change the direction in which you apply the force. The next one, this is an example. The second picture you see over here, this pulley, if you just imagine you're pulling this rope upwards to lift up this load. Now, is this pulley fixed at that position? Obviously no. When you lift up the load, the pulley also is lifting upwards. There's a movement. So this is called as a movable pulley. And movable pulleys always add mechanical advantage in system. So remember, let us say for example, this is 10 kg load. So the tension in this, or the load in this particular say connection over here, that is 10 kg, which is being distributed into these two loads. So you can, in physics, this is called as free body diagram. If I draw a free body diagram of this part, there are two connections over here. They're cut to two threads. This 10 kg has to be equally divided over here. It is 5 kg over here, 5 kg over here. Why equally? Because this is a continuous rope. I told you, in a continuous rope, on two sides for equilibrium, there has to be same load or same tension. So it is 5 kg load distributed on both the sides. So what is the force you're applying? It is only 5 kg of force. You see that there's a mechanical advantage. The load is 10 kg. The force applied is just 5 kg. So there's a mechanical advantage. That you're applying less force to pull up the load of 10 kg compared to the first system. So that's the advantage of movable pulleys, which have a mechanical advantage, wherein by applying less force also you can lift up the system. Now if someone asks you what is the force applied on this rigid support, it will be 5 kg, because ultimately that rigid support is helping or holding a load of 5 kg in this particular connection. So that's how it works. I'm not going into the in detailed calculations. Understanding this basic part, I think, should be sufficient. However, In any complex pulley system, you always can work out using these free body diagrams, and always remember the load has to be transferred equally on both the directions at a pulley, because if it is that is done if it is a continuous rope. So this 10 kg supported 5 kg on both the sides in this movable pulley. One more point to remember, other than force, you have to also remember with respect to distance, the concept itself, this model, like I told you, it is force and distance in pulleys, right? So what is distance in pulleys? So here, let me just summarize and write down the important points for our notes over here. For fixed pulley, so there are two types of pulleys we discussed. For a fixed pulley, with respect to force, it is same as the load. In our example, it is same as load, right? And the second one was a movable pulley. And in our example of movable pulley, with respect to force, we saw it is just half of the load. Now it's not always half. It is a simple setup with one movable pulley, so it is half. There can be complex setups also. We will see how to solve such questions with complex pulleys. That's with respect to force. As far as the distance is considered, let me erase this explanation over here and explain you with respect to the movement in terms of the length, force and distance with respect to distance. For example, if you want to lift up in this fixed pulley, if you want to lift up this 10 kg by 1 meter, you have to also pull this rope by 1 meter. It is the same continuous rope, right? If you want to lift up 1 meter, you need to pull it down by 1 meter. That's where the load will move up. So here, as far as the distance is considered in the fixed pulley, the distance which it moves, that is same as the distance which you pull. Movement in load is same as distance of pull. The distance you're pulling the rope, that is same as the movement in the distance of the rope. In the next case, in the second case, in the movable pulley, remember in this case, if you want the pulley, if you want the load to move up by 1 meter, you need to pull up this rope by twice that length, 2 meter, because it's a movable pulley and the rope is being distributed on both the sides. So if you're basically pulling it by 2 meters, then it will move by 1 meter. If you're pulling it just by 1 meter, the load will only lift up by half meter. So remember, in terms of distance in movable pulley, even though the force required is less, the distance, the time for which you need to pull and the length of the rope which you need to pull, that is double actually here. That's how you are actually getting that mechanical advantage in the system. Even though it's a less force, you need to pull for a longer length, 2 meters it is. So the distance over here, so in the movable pulley, the distance, the movement in load is half the distance of pull. So these are the 2 points you have to remember with respect to these 2 types of pulleys. Quick summary: in a fixed pulley, the force required to lift up a load is same as the load in the simple system setup. As far as the distance is considered, it is also same. So whatever distance of pull you are having, same is the distance of rise in the body. In the movable pulley, force required is half the load, whereas the movement, if you're pulling it by 2 meter, it will lift up by only, it will rise up by 1 meter. So in fixed pulleys, remember, there is no difference in the length of movement and the length of pull. But in a movable pulley, you'll always need to pull it double the overall movement which you want in the body. So that's with respect to distance. So let us look into some past questions of CEED examination, where excuse me, we will work out some questions with respect to these concepts of pulleys, force and distances. So if you look into this question, this is a past CEED question from the year 2022. A system of frictionless and massless pulleys is being used to pull a total load of 2720 newtons. What is the minimum force in newtons required to end the rope? Required at the end of the rope. So basically at this end of the rope, they have shown a force F. They're asking us how much is this force F required to lift up the load of 2520 newtons. So if you observe, how many pulleys are you having overall? 1, 2, 3, 4, 5, 6, 7, 8 pulleys. How many of these are movable pulleys? 1, 2 and 3. These three are movable pulleys. All the other, they are fixed to the rigid support. On the top, that's a ceiling, a rigid support. So this is a fixed pulley, this is a fixed pulley, this is a fixed pulley, fixed and fixed pulley. Fixed pulleys do not have a mechanical advantage. Anyways, let us look into the process to solve this question. First thing first, you can simply draw the free body diagram to understand the overall say distributions, the connections over here. If you say this is 2520, what should be the force in each of this connection to the movable pulley? See, if you are increasing the number of pulleys, obviously the load will distribute on so many pulleys. So if you are if you are putting 10 pulleys over here, the load will be distributed to 10 pulleys. But here the load is distributed onto 3 points, 3 pulleys. So how much is it? There are only 3 connections, right? So if there are 3 connections, you need to divide it into those 3 places. So 2520 divided by 3, it is 840 newtons in each of this. So this pulley is going to support 840 it is, right? So yeah, you will have a scientific calculator on screen in the examination. 2520 divided by 4, you will be getting 840 newtons in this point, 840 newtons at this particular pulley, 840 newtons in this particular pulley as well. So 840 at every pulley, it is 840 newtons. Now at every point, just like the previous one over here, if you draw a free body diagram, if this is 10 kg, it will be distributed equally on both the sides, 5 kg and 5 kg, because it's a continuous rope. It has to be equal on both the sides, otherwise it won't be in equilibrium. So this 840, it will be distributed onto these 2 points. This 840 also will be distributed onto these 2 points. Similarly, 840 will be distributed onto these 2 points equally. Alternatively, you can directly draw a free body diagram through all the supports of it, and you can observe that the load is distributed onto 1, 2, 3, 4, 5, 6 points. So 2520 divided by 6, you will directly get the answer. But alternatively, you can do it stepwise like we have done. 840 first. Now this 840 has to be divided into these 2 equally. So 840 divided by 2 would be 420. So this over here will be 420 newtons. This over here will be 420 newtons. So how much force are you applying? You're applying a force of 420 newtons. You see the mechanical advantage of this system. Instead of 2520, you're just applying 1/6 of it. Why 1/6? Because the load is distributed equally on these 6 points. So whichever point, whichever rope is basically where you're applying the force, that has to be equal to the force in that rope. The rope is basically experiencing 420 newtons. So similarly, if you see, this also is 420, this also is 420. So if someone asks you what is the load at this point in the ceiling, at the rigid support, how much is the force? So it will be 420 over here, 420 over here. So that's going to be 840 newtons. Similarly, you can calculate for all these points, but in the CEED examination, questions are based on logical reasoning and not physics again. So you need not work out the free body diagrams in detail. You can have a generalized understanding and understand the difference between a fixed and a movable pulley, and you can just understand how to divide the load. So I have again, I'm explaining quickly. You have divided this load into 3 pulleys equally. Then at every pulley, because you have a continuous rope, we are dividing it into 2 equal halves on both the sides. Alternatively, you can draw a free body diagram cutting through all these 6 ropes at which the pulley is supported. Now what is the function of the remaining pulleys then? It is just to change the direction, give additional support, change the direction of the force. For example, this force is being applied in the upward direction. If I don't want to work against gravity, if I want to work towards gravity with gravity, I'll just need to add one more pulley over here. Now that will not add any mechanical advantage, but it will change the direction of the force applied at this point, right? So however, the answer for this question, it is a numerical answer type question. The answer is 420 without any decimals as such. The next question, let us look into the next one. This is also a past CEED question from the year 2018. This is based on distance moved. So let us look into it. The image shown below, in the image shown below, this is a multiple choice question. In the image shown below, all pulleys are fixed. If the load needs to be lifted by a height of 8 meters, the load has to lift up by a height of 8 meters. How much distance will the truck have to move? How much is the distance it has to move? And they said all these pulleys are fixed pulleys. Even though it looks as if this is movable pulley, they are saying that it is fixed. So probably they have they have a wall and they have fixed the pulley into the wall. It is not floating, or it's not movable like what it looks like. This also is a fixed pulley, this is fixed, this is also, all these are fixed pulleys, right? Remember, in a fixed pulley, there is no mechanical advantage, as in you don't need less force to lift up a heavy load. Other than that, with respect to distance, also we discussed that in a fixed pulley, the distance of movement or the distance of lift in the load is same as the distance which you move the rope by. So if you want an 8-meter lift, overall you need to pull this vehicle. This vehicle needs to move by 8 meters. Why? What is the reason? Because all these are fixed pulleys. Had there been any movable pulleys, accordingly the answer would have changed. For every movable pulley, the length moving will become double basically. If you have one movable pulley over here, which is probably moving along with the movement of the vehicle, then it becomes double. There will be a mechanical advantage, reducing the force required to lift up the load and also increasing the length. However, because all these are fixed, the answer for this question will be 8, which is option A. This is a past CEED question, simple conceptual one. So remember, if you're having only fixed systems, fixed pulleys in the system, the distance of lift is same as the distance you pull the rope by. Next one. So that was about it. So if you want to practice if you want to have a comprehensive study and practice mainly the sketching questions of part B, if you want to have a special practice on that, the workbooks of arts of KP classes will come in handy for you. We have a set of books for your self preparation and study of CEED and UCEED examination as well, with a lot of practice exercises in these workbooks particularly. So you can purchase the links for all our resources are available in the description of the video. You can check out and have an access to the premium quality resources for your self study moving ahead, particularly the books. So moving on. The third model, as I told you, there are 3 models. The third and final model is belt driven discs and gears. So why am I discussing? So belt driven discs are similar to pulleys. Basically, you have a system of movable discs with some belt, so that's one model. And also gears. However, in gears generally it's not necessary that you have belts in gears. You might have link of chains, like in a cycle, in a bicycle you have gears with the linked chain on which the gears with the help of which the gears move, right? So the concept is same for both these types of questions of movable discs, or say belt driven discs and gears. Let me tell you the concept of it and then we'll solve some questions related to it. The basic concept which you have to remember. Let me talk about discs first. The same concept applies to gears also. We'll solve all the models of questions which have been asked in both CEED, UCEED from gears point of view. But firstly, with respect to discs, let us say there's a small disc over here and there's a larger disc over here, which are both connected with a belt. Let us say there's a belt which passes on these 2 rotating discs. Why do we use this? Basically, in you might have seen in a lot of mechanical equipment, like for instance flour mills. In flour mills you have these belt based discs, wherein one disc is connected to a motor, the other end is where there is some mechanical functioning. Not only that, even in drilling equipment, in all these mechanical equipments we use such systems basically. However, the concept which you have to remember over here is, in discs, if this is rotating, let us say always in a belt based discs, or even in gauge systems, one of it, if there are 2 discs, one will be a driver, the other one will be a driven disc. One is something which you connect to a motor or where you apply force. The other one will be an output part, or it's like input and output. If there's a motor over here and you're turning this disc, the other one will turn as a consequence of it. So this becomes the driver, where you're applying the force or using a motor. The other one becomes the driven disc, right? So these are the terms which we generally use. The relation between the movement between the driver and the driven, it is always this way. So if the diameter of the smaller disc, let us say this is D1, the diameter of the largest disc, let us say this is D2, and if these discs are rotating or the belt is moving, let us say if this belt is moving, if the belt moves, remember the number of turns you see in the smaller disc, the number of turns you see in the larger disc will not be same. If you imagine in this search of movement, the smaller disk has to move a larger number of times for every one cycle of larger disk. If this is rotating one time, to cover the same length of the belt, this has to rotate a lot of times. So always in such systems, the smaller disk will always rotate at a faster velocity, higher speed. So the rotational speed will be high at this point, the rotational speed will be less at this point. So size and rotational speed are inversely proportional, remember that. So the diameter of a disk, it is inversely proportional to the rotational speed, the speed with which it is rotating. That's called as rotational speed. Rotational speed is generally measured in RPM. It is also called as revolutions per minute or rotations per minute, RPM. That's the term we use for rotational speed, which is inversely proportional to diameter of the disk. So let us say if the rotational velocity over here is v1, rotational velocity at this point is v2. The relation between these four values, questions are always based only on this concept in the examinations, where you have to apply this logic of relation between diameter and the velocity. So the relation between diameter and velocity is always this way because they are inversely proportional. So d is inversely proportional to the rotational velocity. This implies d is equal to some proportionality constant into 1 by v. So the v comes to the other side, it becomes d into velocity is equal to constant. The diameter multiplied by the rotational velocity should be constant. In other words, let me use black so that it is clearly visible for you. So basically, the diameter is inversely proportional to the rotational velocity, which implies diameter multiplied by the rotational velocity is always constant. This is the concept we have to remember. So in other words, for this diagram, you can say diameter 1 into velocity 1, velocity as in rotational velocity, which is measured in RPM. That will be equal to diameter 2 into rotational velocity 2. So this is the equation which you have to remember for relation between two belt driven discs. Even for gears it is absolutely same, even in that case. However, in gears not necessarily diameter will be given always. There are questions sometimes where even in gears you have diameter given. If diameter is given, you will apply the same formula. If diameter is not given, you will be using the concept of number of teeth. The number of teeth in a smaller disc will be less, number of teeth in the larger disc will be higher. So you can also have number of teeth in the first disc into rotational velocity of the first gear will be equal to number of teeth in the second gear into the rotational velocity in the second gear. Same concept, but instead of diameter, because see, diameter if it increases, the circumference will increase. It is directly proportional because circumference is pi into d, pi into diameter. So circumference will directly be proportional to it. And if circumference increases, directly proportional to it will be the number of teeth. So because of that, the relation will be maintained same. So you can remember that as an extension to the same formula in terms of gears. But even in gears, many times you apply the same concept because diameter would be given to you. So the simple concept to be remembered is number of turns in the smaller disc or a smaller gear will always be high compared to the other connected larger disc or larger gear with it. And the relation, mathematical relation is given by using this equation of d1 into v1 is equal to d2 into v2. What is d in all these? What is d1 and d2? That is diameter of the disc. What is v1 and v2? That is basically the rotations per minute. Or in other words, you can say the speed, rotational speed of the disc or the gear. So let us practice some questions on these models with respect to belt driven discs and gears. The first question of this particular model, you can see, this is a past CEED question from the year 2013 examination. So a flat belt pulley has a circumference of 40 centimeters. A flat belt pulley has a flat belt pulley, basically pulley is being done by a flat belt. A flat belt pulley has a circumference of 40 centimeters. Let me first read the question and list down the given information. Of 40 centimeters circumference, they have given the circumference, that is pi into d basically. And turns, so remember in this equation, even though I have written in terms of diameter, if I multiply it by pi on both the sides, the equation will not change. So pi into d1 is nothing but circumference of the first disc. This is circumference. So instead of d into velocity, d into rotational velocity, you can also write it as circumference into rotational velocity. So you can also write it as number of teeth into the rotational velocity. Either way, so you can interchangeably use those terms. Do not get confused. However, let us look into it. Flat belt pulley has a circumference of 40 centimeters and turns at 60 rpm. It rotates another pulley of 1.2 meter circumference through a belt having 7.2 meter in length. If the driven pulley has revolved 600 times, so driver and driven, right? I told you those terms. If the driven pulley has revolved 600 times, what is the time the driver pulley rotated? They are asking how much time is the driver pulley rotated. Let us draw a diagram to understand this concept first. There are two discs over here, pulleys basically. A smaller one with a circumference of 40 centimeters. This is the driver. There's a driven pulley of 120 centimeter circumference. So this is circumference already. It's not diameter, it is pi into diameter. Because circumference is 2 pi r. 2r is nothing but diameter. So you can write circumference as pi into diameter. So the pi into diameter 1, that is 40. Pi into diameter 2, that is 120. That's the driven one. And these two are connected with a flat belt pulley, flat belt system. The total length of this rope they are saying is 7.2 meter. However, that's not of consequence in order to solve this question or solve such questions. The length of the belt is unless there is friction to be considered, all these factors do not play a role. So we have to assume that it is frictionless because no other information on friction is as such given. If the driven pulley has revolved 600 times, this is the driven pulley, this is the driver, this is the driven pulley. The driven pulley is rotating 600 times, they are saying. If that's given, what is the time the driver pulley rotated? For how much time are you rotating? How many minutes is this rotating, or is this disc rotating? That's the question. So we basically have two discs, you know the diameter or circumference in both the cases. We'll need to first find out the velocity. So they are saying the only information given is that the driven pulley is rotating a total of 600 times. So this has to rotate 600 times. The number of times the smaller disc will rotate will be much higher for that same 600 times. And also this information is given, 60 rpm is the rotational velocity of the smaller disc. So we have the rotational velocity over here, that is 60 rotations per minute. So we need to first find out the velocity, rotational velocity of the second case. So you know the equation we apply. So you can apply either this d1 into v1 is equal to d2 into v2. If you multiply pi on both sides of this equation, you will get pi into d1, that is circumference of the first disc, into velocity of the first disc is same as pi into diameter of the second disc into velocity of the second disc. Right? So I'm just deriving and showing you, instead of diameter you can use circumference directly. So what is pi d1? What is circumference of the first disc? That is 40 centimeters. Multiply it with the first rotational velocity of the first disc is 60 rotations per minute, 60 rpm. 40 centimeter multiplied by 60 rpm will be equal to 120 centimeters. 1.2 meter is nothing but 120 centimeter. That's the circumference of the second disc. Pi into d2, that is 120, into rotational velocity of the second disc. So what is the rotational velocity of the second disc we are getting? So remember the time for which this rotates, the time for which this rotates has to be same because they are connected with a belt. Overall the system functions for the same amount of time. So that is what we need to calculate over here. So v2 we need to know the value. So that will be 40 into 60 divided by 120. That will give us the rpm of the second disc. How much is that coming out to be? 20. So the rotational velocity of the second disc is 20 rpm. I told you already, the smaller disc will have a higher rpm, larger disc will have a smaller rpm because of its increased diameter. So this is having 20 rpm, 20 revolutions per minute. So basically what is the meaning of it? In 1 minute it is rotating 20 times, 20 rotations. How many minutes are required for 600 rotations? They have given in the question that the disk is rotating 600 times. For 600 rotations, what is the time required? So if this is x simple unitary method, x will be 600 into 1 divided by 20. So the time for which the overall system is functioning, that will be cross multiply 600 into 1 divided by 20. It's like if one apple costs 20 rupees, how many apples can you buy in 600 rupees? It will be 600 divided by 20. That will be 30. So the answer for us will be 30 minutes, which is the second option in the given MCQ question. So the only concept we are applying over here is this: d1 into v1 is equal to d2 into v2, or the circumference of the first disk into rotational velocity of the first disk is equal to the circumference of the second disk multiplied by the rotational velocity of the second disk. So this is how you solve the questions related to belt driven disks. Let us now move on to the next one with respect to rotation, the gears and belt driven pulleys itself. This is a past UCEED question from the year 2022. A system of gears and belts is shown below. The diameter of gears M, N, P, Q, R and S are 3, 1, 2, 1, 3 and 2. The diameters are given in meters. They have given the already, diameters. If the gear M is rotating at 100 RPM, what is the RPM of S? So same logic you need to apply for every two set of discs, the driver and the driven, starting from here. Starting from the first driver, the diameter is given as 3. Let me mark the diameters over here. This is 3 meter, this is 1 meter, the smaller one over here, that's 1 meter, the larger one, that is 2 meters. For P it is 2 meters, then this is 3 meters again, and the last one S, it is 2 meters again. These are the diameters. RPM values, RPM for M it is given the rotational velocity is 100 RPM. Using this we can find out first for N. So for N, how much will it be? So between M and N, I'll just write the heading as for M and N. If you are comparing M and N, for M the diameter, so apply that, d1 into v1 is equal to d2 into v2. What is d1? That is 3 meter. What is v1? That is 100 rpm. Second diameter, it is 1 meter. What is v2? So the velocity of the rotational velocity of disk N, that is coming out to be 300 rpm. That's what we have got from M and N. So let me mark it over here. For N, I'm getting this is the RPM value is coming out to be 300 RPM for N. Now N and P, these are gears. So when you have gears, all the same logic applies. This is the driver now. So first this was the driver, this was the driven. Now this becomes the driver for this driven disk P. So P is a gear which is basically the driven disk. So whenever you have driver and driven, you apply the same logic. So now I'm applying the same concept for N and P, which are also connected gears. For N and P also you apply d1 into v1 is equal to d2 into v2. What is dav1? That is 1 meter into velocity, rotational velocity of the first disk, that is 300 is equal to diameter of the second disk, that is 2 meter. For P it is 2 meter into velocity of the second disk, that is P. So what is the rotational velocity of the second disk P coming out to be? 300 divided by 2. I'm getting it as 150 rpm. So I have calculated for P also. So let me write that value over here. This is coming out to be 150 rpm. Now see, for P and Q, P and Q both are connected together. So when you have two disks or two gears sticking together, the rotation will be same. Even though this is a smaller one, it is not driver and driven, both are stuck together. So basically if N is the driver, P and Q both are being driven at the same rotational velocity. So P and Q will have a same rotation. So you don't apply for P and Q, you don't apply this equation. Why? Because they're not driver or driven, they are both sticking together and moving together. Now moving to the next one. Now this becomes driver and driven. So Q is the driver, wherein the rotational velocity is 150. R is the driven. So now you apply that logic for P and Q and R, because the belt is connected to Q. So for Q and R, Apply the same logic. d1 into v1 is equal to d2 into velocity of the second disk. Diameter of the first disk, that was 1 meter. So you're applying it for q, remember. It is 1 meter, that's the diameter. What is the rotational velocity? It is same as the disk to which it is sticking, that is 150 rpm. What is the driven disk here? That is r, the diameter of which is 3 meter, into velocity of that second disk, that is basically r. So what is the velocity of this larger driven disk r? That will come out to be 150 divided by 3. So that's coming out to be 50 rpm. So you can mark it over here. For r, the rotational velocity is 50 rpm. The last set is for r and s, the driver and driven concept you apply again. So let me write that over here. I'll do the last set of calculation over here. R and S, apply the same concept. d1 into v1 is equal to d2 into v2. The driver, that is having a diameter of 3 meter. What is the rotational velocity of the driver? It is 50, is equal to 50 rpm basically. What is the diameter of the driven disk? That is 2 meter, into the velocity, rotational velocity of the driven disk. Rotational velocity of the driven disk, that is basically s, that will be equal to 3 into 50 divided by 2. So 3 into 50 is 150, 150 divided by 2 is 75. So velocity, rotational velocity of the last driven disk, that is s, that will come out to be 75 rpm. Remember, in the examination you will not have so much of time to slowly think and attempt the question. If you know the concept, if you just know the simple concept of driver and driven, what is the relation between driver and driven? Always diameter into velocity is constant, or circumference into velocity is constant. So if you apply this concept for driver and driven for any two pairs of this, if you know that concept, it will hardly take you a minute to do the same step 3 times, 4 times. You'll get your final answer. So the answer for this question is going to be 75 rotations per minute, 75 rpm. That's the answer for this question. So that's how you answer these questions of belt driven discs and gears. Let us look into the next 1 or 2 more questions of this model probably, and then we'll end the lecture with it. So this is a past CEED question from the year 2021. Gear Q is fixed on a pulley. Gear Q is fixed onto a pulley R. If pulley P, so it's a combination of pulley and gear both, you see over here. If pulley P undergoes 4.5 full rotations, P is undergoing 4.5 rotations. It can be rotations per minute, or we don't know the time, so you can say per unit time basically. So you can count it as 4.5 rpm itself. It will be easy for us to answer the questions that way. So 4.5 rotations, full rotations. How many rotations will S undergo in the same amount of time, right? Because see, even though they have not mentioned same amount of time, I'm assuming it is rpm instead of rotations, because both are related. So what are they asking? They're saying this pulley P is rotating 4.5 times completely. How many times is S going to rotate completely? That's the question they're asking. Now we obviously know that the complete system will function for same amount of time. Let us say the time required for that 4.5 full rotations is 1 minute. So it will be easy for us from terminology point of view. So the RPM is, let us say, 4.5 RPM. All the diameters are given. We apply the same concept. D1 into V1 is equal to D2 for driver and driven. First apply for the pulleys, then it gets combined to the gears moving further. First let us do it for pulleys. For P, let me mark, P, Q, R, S are already marked. So let me mark this as T, this as U. I think that should be sufficient because this is after the gear, so this is not necessary for us ideally. I have marked the names as T and U. Let us apply the same concept for any two driver and driven pulleys. So P, let me apply the concept for P and T first. If you consider P and T, the diameter of P into the rotational velocity of P is equal to diameter of T into rotational velocity of T. What is the diameter of P? It is 40, probably centimeters. They have not marked the units, so I'll just write it as 40 into rotational velocity of P is 4.5 is equal to diameter of T is 20 into rotational velocity of T. So what is the rotational velocity of T coming out to be? It is coming out to be 4.5 into 2, that is 9 rotations per minute. And even though it is 9 rotations, I'm considering it as rotations per minute for ease of calculation. or the use of terminology. I have got 9 RPM in T. So what do you observe? If the diameter is reducing by half, if it is becoming half, the RPM is getting doubled, right? Directly proportional. Next one. So these are some intricate. Once you have sufficient practice, you need not do the same calculation again and again. So if the diameter is becoming half, the RPM value is becoming double. Even in the same concept, you can apply in the previous one. If the diameter is becoming 1/3, RPM value will increase 3 times. Same logic you apply over here. Even without doing the complete sequence of step of maths. So dia is becoming half, 9 RPM. Next the dia is becoming half again, so from 9 it will become 18 RPM. This is the driven. Now from the larger disc, so comparing the smaller disc and the larger disc, the diameter is becoming 40, it is increasing 4 times. So this RPM value will reduce by 4 times, so it will become 18 by 4. 18 upon 4 should give you again 4.5, right? So this will be 4.5 RPM. So because P and R are both of same size, if this is 4.5 RPM and they're interconnected, this also will have same number of turns of 4.5 RPM. And the same concept like previous one, here the pulley R, the disc R and the gear Q, they are fixed together. So you don't apply the driver and driven concept, they are together moving. So if this is 4.5 RPM in the disc R, you will have same 4.5 RPM in the gear Q also. So you just need to apply the concept of driver and driven for Q and S. So Q, the diameter is given as 20. For R, the diameter is given as 40. So the diameter is getting doubled. So if the diameter is getting doubled, RPM value will become half again. So the answer finally for S, the rotational velocity will be half of 4.5, which will be 2.25 RPM or 2.25 rotations. That's the final answer. However, if you're not very clear, let me apply the math and do the math and show you by applying the formula for Q and S. For Q and S, diameter of Q into rotational velocity of Q is equal to diameter of S into rotational velocity of S. What is diameter of Q? It is 20. What is rotational velocity of Q? It is 4.5. Because it is stuck to R and R has 4.5 rotations. That should be equal to diameter of S, that is 40 again, and the rotational velocity S is over here. So this cancels out 2 times. Rotational velocity of S will be 4.5 by 2, which will be 2.25 rotations. Same answer. So 2.25 is the answer. Whenever you have decimal points in the answer, there will be a short range given. The official answer key for this question is 2.24 to 2.26. That's the range given in the official answer key. So 2.25 is the exact correct answer for this question. So remember, if the diameter is getting doubled, rotational velocity will become half. Similarly, if the diameter is becoming half, rotational velocity will increase 2 times, it will become double. So that's the relation between one and the other. Let us look into the next question. This is a past UC question from the year 2017. Two gears A and B with red arrows are shown below. Gear A rotates in the clockwise direction. They have marked the arrow over here. How many complete rotations does B have to make for the red arrows to meet? So there are 2 red arrows. One is marked in the depression, the other is marked in the teeth. When is this teeth going to fit into this exact same depression? That's what they're asking. The first step you need to know is how many depressions are you having in B? You have 1, 2, 3, 4, 5, 6, 7 and 8. So there are 8 depressions in B. So after every one cycle, the next 8th teeth will come into touch, right? Every cycle, 8th teeth will come into touch. And if you observe in the diagram, at a given point, only one teeth is in contact with the smaller gear, and every 8th teeth will come into contact. You have to keep on counting how many cycles of those 8 are required to end at this red arrow. So let me give you an example. So we start with this. So this is already in contact. You start with this particular one. This is 1, 2, 3, 4, 5, 6, 7, 8. So after one complete cycle of the smaller gear, this teeth will come into contact, right? So that's the teeth. Next again, you will start with 1. After one more rotation, again the next 8th stop or eighth teeth will come into contact. You keep on counting. So that's one rotation we have added. Next rotation, this you'll again start with 1, 2, 3, 4, 5, 6, 7, 8. This teeth will come into contact after the second rotation. So you have to keep on counting the number of rotations and see at which point will you stop at this red arrow. That's how you need to solve it. So let me keep on doing that. This is 8 again. Let me start with 1. This is 1, 2, 3, 4, 5, 6, 7, 8. After the third cycle, this is the teeth which will come into contact. After next rotation again, 1, 2, 3, 4, 5, 6, 7, 8. This teeth will come into contact after the fourth cycle. I'm marking stars, so let me see at which point, after how many times will the star end at this red arrow. Right, so this is 1 again. 1, 2, 3, 4, 5, 6, 7, 8. So we are going to stop over here after the fifth rotation. 1, 2, 3, 4, 5, 6, 7, 8. This teeth will come into contact after the sixth rotation. 1, 2, 3, 4, 5, 6, 7, 8. This teeth will come into contact after the seventh rotation. 1, 2, 3, 4, 5, 6, 7, 8. This teeth will come into contact after the eighth rotation. 1, 2, 3, 4, 5, 6, 7, 8. This teeth will come into contact after the ninth rotation. 1, 2, 3, 4, 5, 6, 7, 8. We have stopped at the 8th arrow after the 10th rotation. So how many rotations are required for us to have this red arrow teeth to fit into the same depression over here? 10 rotations are required. So this is a numerical answer type question with 10 as the answer. So simple logic based question it is, without any numerical calculation as such. Next one, this is also conceptual one. It is an MCQ question from past CEED 2024 question. A simple one. Let us look into the concept. A cyclist was pedaling a geared cycle on an upward inclined road and decided to stop on the incline. Which option can be used to stop on the incline only using force on the pedals, without applying or without pedaling, just by applying force? Which position can stop? So basically the driver and the driven, you're applying for the pedal is the driver here, you're applying force on the driver. Which position will apply a higher force on the driven wheel? The driven wheel is the wheel, basically the one which is connected to the tire, the back one, right? So if you observe the four options here, the driver is a larger one, the driven is a smaller one. You're applying force on a larger one and that is stopping a smaller one, right? So basically force will induce some velocity, right? So when will it be easy for us to stop the vehicle, stop the cycle? That's what they're asking. Should the driver be small or should the driver be large? If you compare all these four options, here both the driver and the driven are of same size in option C. It means if you apply some force, same amount of force will also be applied on the back tire. Probably the cycle can stop, but the force required will be very huge and humanly could be impossible to. So you're not using any mechanical advantage over here. So this cannot be the answer, because the force applied and the input and output are same. So you have to select an option where input is less, output is more, right? Here the driver is large, the driven is small. So the input will be higher, the output will be less. So this also cannot be the answer. Here the driver is large, the driven is small, right? So again the input you're putting in, that is very high, the output you get, that is low. That also cannot be the answer. Here the driver is small, the force you're applying, that's on a smaller gear, the output is larger, the driven is a larger wheel. So the answer for this question will be B. So basically you can stop the bicycle when the driver is small and the driven is large. Just by applying force you can stop the cycle. So the answer for this question will be option B. The next one, this would be the last question of this concept of this topic. This is a UC 2017 question, MCQ 1. Similar concept again. If gear P is driving gear and rotates clockwise, this rotates clockwise, which of the following statements is true? Q rotates clockwise, S rotates anti-clockwise. So basically there are questions where they're asking the type of rotation of all the gears. So let me mark them and see which options are correct. This is a multiple choice question, only one statement will be correct. So this P they are saying is clockwise. So similar to how we have looked into in pulley, same concept will apply for gears also. Now, if this is rotating clockwise, this rod or this particular vertical line that should shift downwards, if that is being pulled over here, this will rotate in anti-clockwise direction. This will be anti-clockwise. If this is rotating anti-clockwise, this rod has to move upwards. Now, if that is being pulled, the rotation over here will be in this way. That will be a clockwise rotation. If this rotates clockwise, the pulley on it, so if this is basically pulling it, or if this gear is basically moving clockwise, this will move in the anti-clockwise direction. Always two connected gears, they work this way. If one is moving clockwise, the other one will move in the anti-clockwise direction. Now if this is anti-clockwise direction, this rod has to move, or it moves in this vertical direction upwards. If that is moving upwards, the gear over here T, that will move in the clockwise direction again. The next one, if this is clockwise, this has to be anti-clockwise. Let us see which statements are correct. First statement, Q will rotate clockwise. Q is anti-clockwise. So A is an incorrect statement. B, R and T both will rotate anti-clockwise. R is clockwise and T also is clockwise. So this is also incorrect statement. R will rotate clockwise, R will rotate clockwise, and U will rotate anti-clockwise. U will rotate anti-clockwise. So this is a correct statement. C is a correct statement. Let us check option D also, just to be sure of our answer if we have done it correctly or not. S will rotate anti-clockwise. S will rotate anti-clockwise. U will rotate clockwise. No, U is anti-clockwise. So that's not correct. So answer for this particular question is C. I hope the concepts of pulleys and gears is clear for you. The three models of questions we have covered in the lecture, I hope that is clear for you. For additional practice, you have access test already uploaded on the mobile app. You can practice the questions over there for this particular day 17 lecture, and then move on to the next day, that is day 18. So this is the procedure you have to follow: lecture, notes, practice questions, and then move to the test of that, then move on to the next day's lecture. So if you're going to follow that approach for all the 71 days, you'll be in a position to clear the CEED examination with a wonderful result. All the best from our end, and we'll meet you on the next day's lecture later on.